This hit and run is about curing multicollinearity. Hey, we have learned the definition, we've learned the consequences, we've learned how to detect it. Now let's see how we can cure that multicollinearity. Do nothing. Oh, wow. Isn't that a disappointment? Because in our culture, our idea is if we find a problem, we've got to fix it. Well, sometimes the best cure is not actually a cure at all. It's to do nothing because all of these cures I'm going to show you have disadvantages. So sometimes you just come to the end of it. You throw up your hands and say, well, we're going to do nothing. Drop one of the multicollinear variables. Remember, our problem is that we have two explanatory variables that are highly correlated with each other, perhaps even more so than they are with the thing that we're trying to explain. So we just drop one. The redundant one, if known, hey, if you've got two redundant variables like the number of toners sold by an office machines company and then the number of cases of toners sold, well, one of those is going to be redundant because they're both measuring the same thing. But hey, this is not usually going to be a very good cure because if you had totally redundant variables in your model, you already got rid of them. But obviously here, if you have a redundant variable that's not adding anything, just drop it out. The problem with dropping one of the multicollinear variables is that will generally lead to bias if the omitted variable is in the true model. So in that classic example of age and education, if both of them contribute to explaining the salaries at a firm, if you drop age and leave in education, then you'll exaggerate the effect of education. Hey, if you drop education and leave in age, then you'll be showing some really big seniority premiums, but in both cases you'll be wrong because you will have a biased estimate. Transform the variables. Hey, here we get to do some wizardry. So let's form a new variable. That would be one way to do it. And let's say that we're doing an equation that attempts to explain the salaries of movie stars. Hey, you're like Jennifer Lawrence. There's been some public controversy about how much money she makes compared with others. Oh, you've got to see her in Winter's Bone. Yeah, it's one of her very first film. That's Winter's Bone. Go check it out. Great film that respects people who live in rural poverty. Really engaging film there. Well, one of the things that would determine what Jennifer Lawrence gets paid for starting a new movie would be home video sales. So we got this home video variable. And the thing is, we'd really like to know, well, does her popularity on streaming have a bigger influence than her popularity on, let's say, Blu-ray, which is still a technology of choice for people who are collectors? They'll have the complete Jennifer Lawrence set. And so we'll have these two different variables. And guess what? Streaming revenue for a given movie star is very highly correlated with Blu-ray revenue because, hey, if they're really popular, both are high. If they're not very popular, both are low. So here's what we could do. We could form a home video variable that is equal to the streaming revenue plus Blu-ray. Okay, like that. And when we do that, then we'll no longer have a collinearity problem, a multicollinearity problem between streaming and Blu-ray. However, you notice we will not then be able to get the separate effect of streaming and Blu-ray. It'll just be $1 of home video sales and how that translates into earnings on a new movie. So yeah, you can form a new variable, you throw away a little information there, but it might be a way to get rid of the multicollinearity. The next thing you can do is difference the data if they're time series. So if we have time series data, look what we can do. We can form a variable called y star sub t, which is equal to our original yt, and then we just take the previous year's value. So that's minus y in time t minus 1. Notice that if what we're trying to explain here is gross domestic product, then we won't have just gross domestic product as our dependent variable anymore. Instead, it'll be the change year over year or quarter over quarter in gross domestic product. And so instead of getting a number way up here in the trillions, that native variable, we're going to get a number much smaller than that, which just represents the change from one year to another. Then out there, for all those xj's in time t, all of those explanatory variables, we're going to take each one of those and we're going to subtract this times value minus xj, the previous times value, xjt minus xj in time t minus 1. Notice that we now have a new model, and now we're modeling the change in GDP as a function of maybe the change in consumption, change in interest rates, whatever explanatory variables that we have over there. Now, this is a great cure for multicollinearity, but now you've got a different model with a different interpretation. Oh, and let me just tell you, time series is an art all unto itself. So a lot of schools have a separate time series class, as we do. Recommend you take it if you're interested in time series. But in addition to solving the multicollinearity problem, this time series differencing will often solve some other problems that are unique to time series. So there is that possibility to difference the data if they're time series. Having differenced it, you just run your new dependent variable against all of your new explanatory variables. Take logs of data. In our next section, we're going to spend some time on this. If you take the log of a dependent variable, say like log of y, and then run it against the log of x, maybe a bunch of different x's if you've got them out there, then running log of y against log of x may cure your multicollinearity. It shrinks the scale of everything, and it may also cure heteroscedasticity. Now, that's another story, but a lot of people take logs for that reason. So then, obtain more data. Yeah, obtain more data. Now, notice you could always say that because there's hardly any regression study out there that wouldn't benefit from more data. But in the case of multicollinearity, this is not a dumb answer. It's not an empty answer. Because if your problem is that you're studying the salaries at one branch of a firm, and all of the people with higher education at that branch of the firm are people who are also older, then your multicollinearity problem is going to prevent you from disentangling those two things. But if you expand the study to the entire firm, well, that might include a branch where you've got some young whiz kids with PhDs, a lot of education, low age, and maybe, the 65-year-old cleaning crew member who doesn't have much. And the additional data will allow you to disentangle the effects of education and age. However, if you're doing a regression study, typically you've already got the best data that you can get. You've already dropped multicollinear variables, so you're kind of left with the transformations or dropping one of the multicollinear variables. Okay, all this is why we say that the cures for multicollinearity may be worse than just leaving it alone, and that's why doing nothing is really not a crazy answer. So that is the hit and run on curing multicollinearity.